Thank you. And next, I'd like to welcome Diego Sanchez, KD2 RLM. He'll be talking about the climatology of traveling ionospheric disturbances observed with reverse speaking network and WhisperNet. Thank you, Diego.
Thank you, Nathaniel. Hi, everyone. Yes, so this is on my study on Nathaniel's new observation technique using RBN ham radio data networks to detect traveling ionospheric disturbances. So just to go through real quick what Veronica went through earlier, in case anyone new came in, traveling ionospheric disturbances, they are quasi-periodic variations of F region ionospheric density, and they have profound effects on radio propagation. For this study, this current technique can only really observe LSTIDs, large-scale traveling ionospheric disturbances. They are TIDs with wavelengths of over 1,000 kilometers, periodicities of between 30 to 180 minutes, and they are often caused by auroral electrojet enhancement and particle precipitation. The current instruments that we have to observe these are SuperDARN radars, GPS TEC plots, total electron content plots, and ionosondes. So just to illustrate real quick what happens when a traveling ionospheric disturbance goes through the ionosphere. As the ionosphere becomes perturbed, you could see that the refraction changes the actual distance, propagation distance. So this is what we're looking for in these instruments. These are usually perceived as a type of HF fading. And the data that we use for this study, we used amateur ham radio observation networks. For this study specifically, reverse beacon network, WhisperNet, the weak signal propagation reporting network, and a PSK reporter. These are networks of stations that record ham radio usage data in real time. So here we have a visualization of the ham radio spot data. This one specifically is using RBN and WhisperNet. So we have AB on the very top. These are showing geomagnetic storm indices and solar activity from the GO satellites. These are kind of to eliminate any disturbances that we might find in the ham radio plots that might not be directly related to TIDs. On the bottom left corner, over here, we have the location of the spot data from these networks. For this plot here, we're only looking at the continental United States. And over here in C and D, for 14 and 7 megahertz, we have ham radio spot data over a 24-hour period. And our y-axis is the propagation distance between transmitter and receiver. The color is showing the actual amount of spots for that time of day for that distance. And what we're looking for are these wave-like structures that appear in some of these plots. These are indicative of potential TID activity. You can see as you go through, the overall minimum distance is changing for the entire United States. And so Nathaniel's paper, he just got it published, detailing this new technique that he developed. So we took these observations and we compared them to other existing instruments for the same day where we found these same structures. So we have on top here, this is using RBN, WhisperNet, and PSK reporter for the 3rd of November 2017. There's a very clear wave structure going through the data. Down here we have for the same day using SuperDARN data, and you can see the very similar wave structure at the very same time of day. And down here, one of the other instruments using GPS TEC plots, very similar wave structure. So these plots, the TEC plots look at average total electron content over time. You can see that the average total electron content is changing very similarly to the wave structure that we see in the ham radio data. So once we had this new technique showed we could see the same structures from other instruments, I went ahead and I plotted for the entire year of 2017 daily ham radio plots, and I searched them individually for any TID structures in them. And I was basically finding any days that were clear, quiet days where it was very flat with no activity or with TID structures, and I was eliminating any days, as you can see here, that had very significant amounts of geomagnetic storm activity or solar flare activity, which would generally cause very large blackouts, as shown here, of the ham radio data. So initial results that I have for the year 2017, I observed a lot more TID activity during the summer months as opposed to the winter months, with a slight enhancement in the month of June. We still don't quite understand why that enhancement in June, but for the most part, much more activity during the winter months. This here for Europe, and then I went ahead and I did it for the US as well, and again, very similar results, much more TID activity during the winter months. And just to kind of eliminate the possibility that these seasonal patterns could be caused by any overall ham radio operators maybe changing the amount that they actually use during compared to the time of year. So I found the average amount of spots per month for the entire year of 2017 using RBN and WhisperNet, and didn't find any significant seasonal patterns within them. And so the next thing I did, I went and compared this to a previous paper, 2014 paper by Nathaniel Fursell, using SuperDARN data for MSTIDs, medium-scale traveling atmospheric disturbances, and found very similar patterns. So he found that there was much more activity for TID events during the summer months as opposed to, for winter months as opposed to summer months, which is very similar to my results. An interesting thing is that SuperDARN has very limited summertime observation capabilities due to a lack of ground scatter, which is not a problem that we see in the ham radio plots. So during the summer, since we see much more TID activity during the winter months, we expect to see more quiet events, so days where there was no noticeable disturbances in them during the summer months, which is not something that SuperDARN, as you can see here, can really see, but the ham radio data is actually able to see that for the summer months. And next we started looking for the potential sources for the TIDs that we were observing, and one of the main sources that we're looking at was auroral electrojet indices. So we have here the Max Kyoto AE index. This is again from Nathaniel Fursell's 2014 paper. He found that there was a slight enhancement. So we see over here for TID events, we have that the overall Max AE values are higher for TID events as opposed to days where we had quiet events. And I found very similar results with the ham radio data. So for TID events, we had slight enhancements of Max AE as opposed to quiet events, which was much closer to values of 0. So conclusions, future work, found that TID activity was much more prominent during the late fall and ending in early spring. The ability to make observations during the summer months for ham radio data. We're currently limited to LSTID observations just because of the nature of the data and the technique itself. The ham radio overall traffic was not noticeably influenced by season, and we still don't know the exact mechanism. We're still looking at others like geomagnetic sources and neutral atmosphere, but we have found slightly enhanced Max AE values for TID events. Thank you. Any questions? Yes.
How large are these waves that you're seeing?
These LSTIDs, over 1,000 kilometers size. Anyone else? Yes.
Just quick, again, what is the data that you're processing? Is it signal to noise ratio data or signal strength data?
Well, I know.
Just contact showing up.
Yeah, contact and distance.
Okay.
Right, that was all the information.
Yeah, just contact. Do you hear them or not?
Okay.
Anyone else?